So welcome to the Ekeeda live sessions, YouTube live sessions. So we are doing the gate doubt clearing live sessions for the subject of steel structures. Right, we have already completed one first session last Monday. Now today it's the second session. So here today we will be majorly discussing about the test solutions. This test was conducted on the Ekeeda app. For the people who are new, you can download the Ekeeda app from the Play Store, or you can find the link on the description box above. So you can download and get access to the complete GATE course, academic course, professional course. For all the courses, you can download our app. We have recorded sessions for all subjects for different number of hours for all the branches of engineering. Also, what we have is we have notes, live doubt clearing sessions on YouTube classes for the recorded sessions. And we also give assistance, internship assistance and job assistance. Newly we are coming up with that particular uh, profile. So for the people who don't know uh, about the app, what you can do is just go to Play Store and download the app, and you can use Gold 11 code. Hello Tanvir, welcome to the class. So you can use the Gold 11 code to get a complete 3 days access uh, of all the courses on the Ekeeda app, so that you can go through and select. So we have three different passes: silver pass, gold pass and platinum pass, which you can purchase. So based on the different passes, different access will be given to you accordingly. So this passes, or there are individual subjects also you can go. Please download the app and go through. You'll come to know all the details about it. This is for the people who are new. So let us start with today's session. So we had a test conducted yesterday, that is on Sunday, on the Ekeeda app for 20 marks under the topic of plastic analysis. So we had 10 questions for 1 mark, and we had 5 questions for 2 marks. So this total 20 marks was conducted on the plastic analysis of beams. So we will discuss the test questions today. So if time permits, we also will see a problem on bolted and welded connection. It depends upon how much time we have for the entire class. Okay, so let's get started. So this was the first question from the test. So what is being asked? The plastic. So already the details on plastic analysis of beams we have done in our previous lectures, right? You can go through the recorded lecture if in case you have any doubts, or what you can do, you can go for the course of steel structures, gate steel structures in the app, and get the complete access. Okay, so today basically we'll do the test solution. So what does it say? Whoever knows the answers can comment in the comments live session, so that I'll come to know. If you don't get it, it's okay, I will be explaining you the process. Okay, so what does it say? The plastic section modulus for a rectangular section of breadth B and depth D. See, generally there are two types of section modulus. Section modulus is generally kept as Z. So one section modulus is elastic, and the other section modulus we have is plastic section modulus. Now how do we get elastic section modulus? It is nothing but I by Y max. How do we get the plastic section modulus? We get the plastic section modulus by taking into A by 2 YC bar plus YT bar. Now this is particularly for the rectangular section. Okay, so complete theory has been already dealt in the previous session, so you can go through that if in case you have any doubt. So basically what plastic section modulus does is it divides the section into two equal halves. Okay, so it divides the entire area into two equal halves. Okay, now how do you calculate? Now this is what a rectangular section. He's asked plastic section modulus. First of all, let me tell you elastic section modulus also, so that we can have a discussion on that. So elastic section modulus is I by y bar. So say suppose this is my rectangular section. Okay, so this is breadth is b, depth is d, and here the neutral axis will lie exactly at the center, right? And this one is what? This one is your uh, d by 2. Okay, so now this I is nothing but bd cube by 12 for a rectangular section, and y max is nothing but the distance from the neutral axis to extreme fiber. Whether we go for top fiber or bottom fiber, both the places it is d by 2. So what will we get? Bd square by 6. So this is what your uh, ZE. Now, when we go for ZP, first of all, what we have to do is we have to locate, see, this is your elastic neutral axis. Elastic neutral axis generally passes through your center of gravity or CG. Now, when it comes to plastic neutral axis, I told you here the plastic neutral axis I'll call is it as YP bar, and the elastic neutral axis I'll call it as YE bar. Okay, just for understanding. So this passes through the CG, and this divides the entire section into two equal halves. Now, in this particular case, because the section is symmetrical, your plastic so your plastic section modulus will divide the area into two equal halves. So here exactly is your plastic section modulus. Now from here, say this is my compression zone and this is my tension zone. So for this particular distance is YC bar and this particular distance is YT bar. Okay, so only for the upper portion this is your CG and only for the lower portion this is your CG. So how much will this be? This also will be D by 4, because how will we get D by 4? D by 2 by 2. That is how you will get D by 4. Here also what you will do? D by 4 you'll get, how will you get this again? D by 2 by 2. Okay, so if you put it in this formula, what will be your ZP? ZP will be area by 2. Area is nothing but B into D for this rectangular section by 2 into YC bar is D by 4 plus D by 4. So on simplification, what will you get? By 2, this will be 4 will be the LCM. So D plus D, it will become 2D. This and this will cancel. So you will get what? BD square by 4. So what will be your correct answer? B is your correct answer. Okay. So this is how you can get your plastic section modulus for the rectangular section. So if they ask you elastic section modulus, how much is it? It is BD square by 6, and plastic section modulus it is BD square by 4. Okay, in case they ask you shape factor S, shape factor, in case they ask you what is shape factor, your ZP by ZE. So it will be BD square by 4 whole divided by BD square by 6. So this and this will cancel out. This will be 2 and this will be 3 ja. So you'll get 3 by 2, which is nothing but 1.5. So for a rectangular section, ZD is equal to BD square by 6, ZP is equal to BD square by 4, and your shape factor S is equal to 1.5. You can remember these standards. If in case you don't remember also, this is how you will have to derive it. I hope you have understood. Okay. So let us move on to the next question. What does the next question say? So if YY is a centroidal axis of the T-beam, so this is what? This is your centroidal axis. The section given us to us is a T section. So if you observe, T section is a unsymmetrical section about your y-axis. Suppose you take, sorry, unsymmetrical section about your x-axis. Suppose you take y-axis, it is symmetrical. Okay. So T section subjected to plastic moment MP. So MP is the plastic moment. Then the neutral axis lies. So where exactly the neutral axis will lie, he is asking you. Okay. So above the line ZZ, between the line XX and YY, between the line YY and ZZ, below the line XX. Okay. So, so generally, see here this the very important thing to be noted is this. The plastic moment MP. He's asking you about the plastic moment. Now, when the section, any section has entered into the plastic zone, what happens is we will have to calculate the plastic neutral axis. Where does the plastic neutral axis lie? The plastic neutral axis divides the complete area into two equal halves. Now in this case, when you observe, the on top of this area is more, right? I will do one thing. I'll call this entire area. Okay, let for more simplified version, I'll call this entire area as this one as A1. Okay, up to this as A2, up and this as A3. So what happens is from the figure only you can see that A1 plus A2 is greater than A3. Okay, so what I have to do, I have to shift this centroidal axis upwards. See, generally your Y bar of elastic, that is the elastic neutral axis, is lower when compared to your plastic neutral axis, or what you can say is the depth of the elastic neutral axis is greater than the depth of the plastic neutral axis. So if elastic neutral axis is here, when it comes to plastic, obviously this depth has to reduce. So if the depth has to reduce, where should the neutral axis go now? The neutral axis should shift towards the top. Say now this is your YE bar and this is your YP bar. This is standard. Okay, this is a standard way, or general, or in general way you can take it like this. So A1 plus A2 is greater than A3. That's the reason we have to shift the neutral axis in between somewhere in between A1 and A2. So it is going to go up. So what will be the exact answer? Hello Ahmad, welcome to the class. Happy to hear that. Okay, chalo. So the line lies between YY and ZZ. So this is your correct answer. Okay, so this is the logic you can remember for all the unsymmetrical sections. If it is symmetrical sections, they both will coincide. For symmetrical sections, let me put a note for you. For symmetrical section, Y elastic is equal to Y plastic, and for unsymmetrical sections, Y elastic will be greater when compared to Y plastic. Okay, so this is the note what you can make. Okay, chalo. Let's get going to the next question. I hope the concepts are getting clear to you. Okay, so a cantilever beam of length L and the cross section with shape factor 1.5. So the shape factor here is given as 1.5. The length is L. Supports a concentrated load P as shown in the figure. So this is a fixed beam, right? It has a concentrated load like this. The length LP of the plastic zone, when the maximum bending moment equals to the plastic bending moment, will be. So generally we know that, see, very important for you to understand this. So how will the diagram, how will the bending diagram for this beam will look? So like this. it will be like this. Okay, so this length is L. Okay, now here for this entire length L, the plastic moment will be MP, and for this length LP, that is the length of the plastic zone, the moment will be M. Okay, so what he wants, he has also given you the shape factor. The shape factor given for you is how much? 1.5. Generally, what is shape factor? MP by M. Now, when you take it to corresponding to length, for MP, the length is L. For M, the length will be L minus LP. Okay, now compare these both. So, if in case I take 1 by F, this will be what? L minus LP by L. What I will do is I will take L out common for both the things. I'll take it as denominator. Okay, I'll cancel it out. 1 minus LP by L. Okay, that is nothing but 1 by F. Basically, I have to get the value of LP. Okay, my intention is to get the value of LP. When the maximum bending moment, so he wants the length of LP for the plastic zone. I have just randomly taken LP. We don't know what exactly is the value of LP. So what we are trying to do, we are trying to consider the shape factor and do it. So shape factor has two definitions. One is the plastic movement by the elastic movement, or we can call the plastic section modulus by the elastic section modulus. Okay, I am trying to use the first relationship. Okay, so send this on other side and send this here. So LP by L equal to 1 by 1 minus F, and finally what will be a LP? 1 minus 1 by F into L. So this will be what? 1 minus 1 by F is 1.5. So how much it will be? 1 divided by 1.5 will be 0.6667. So 1 minus 0.6667 into L. So that will be 0.333 L, or what you can do, 0.333 is nothing but 1 by 3 of L, because it's a recurring value. So where does the till where does the plastic zone lie, or what is the length of the plastic zone? It is 1 by 3 of L. Likewise, for different shape factors, you can find the value of the plastic length or plastic zone. Okay, so what is the answer? Do we have the answer given to us? Yes, actually, these options are slightly wrong. So this should be L by 3, L by 4, L by 3, 2L by 3, and L by 2. In case you are not able to understand, L by 4, L by 3, 2L by 3, and L by 2. So what is the correct answer? The correct answer is option B, which is L by 3. In case I change the shape factor uh, to 2, what will happen? Let me just do it. In case I change this shape factor to 2, what will happen? So here in place of 1.5, just take it as 2. So it will be what? Here 1 minus 1 by 2. This is nothing but 0.5 of L, or that will be L by 2 in case the shape factor is equal to 2. Okay. Next, moving on to the next question. What is the next question? They say the shape of the cross section which has the largest shape factor. So out of all this, the shape which has the largest shape factor is being asked to you. Rectangular, I section, diamond section, and solid circular. So the correct answer for this is the diamond section out of all this. So if in case you want, what do? You just by heart the standards, okay, for a rectangular, or what you can do, you can just anytime calculate using the formula shape factor F is equal to ZP by ZD. You know how to calculate elastic section modulus, you know how to calculate plastic section modulus, just do it. Okay, so for rectangular section it is 1.5, for symmetrical I section it is 1.14, around 1.14. Okay, I'll write like this. Then for diamond it is 2. Then for a triangle, actually for triangle it is the highest, but in the option there is no triangle, so I have chosen the diamond. Okay, and for circle it is 1 by 1 point, sorry, 1.7. Okay, so these are the standard shape factors. Shape factors generally depend upon the dimension. Okay, it doesn't have any unit, so you can by heart these standards to get any question out of these. Okay, chalo, next, fifth question. What is it asking? What is the question demanding? What will be the plastic movement capacity? Okay, what will be the plastic movement capacity? See, generally your M is nothing but ZE into Fy. This is elastic moment, and if you want plastic moment, it is Zp into Fy. Okay, so if you know the shape factor and Fy is a material property, it will be given to you in the question. So if you observe here, Fy is given to us. How much is Fy? 250 Newton per mm square. They are asking us the plastic moment carrying capacity MP is equal to question mark of this rectangular section of size. So the size of the rectangular section is breadth is 500 mm, the thickness is 100 sorry 10 mm about the XX axis. Okay, now your duty is to find what, where exactly is the plastic neutral axis. First you have to find plastic neutral axis, then you have to find the value of Zp, and then you have to find the value of what, thirdly you have to find the value of the MP. So first of all, this is a symmetrical section, right? If it is a symmetrical section, where will your plastic neutral axis lie? It will lie exactly at the center of the cross section, because it has to divide the area into two equal halves. So due to symmetry, what will happen? Due to symmetry, the plastic neutral axis is at mid depth, right? So your AT will be equal to AC will be equal to BT by 2. Here instead of depth they have given us thickness. Okay, so the force, this force will be how much? This force will be what? Area into the Fy. Now what will be MP? Force into perpendicular distance. So here to here, okay, here to here, this is nothing but T by 4, and this is also nothing but T by 4. So in total this will be how much? T by 2. T by 2. That will be what? BT by 2 into Fy into T by 2, which is nothing but BT square by 2 into Fy. What do you remember? What is BT square by 2? No, not 2, 4. BT square by 2, because this 2 to the 4 it will come. Okay, that is nothing but Zp no for the rectangular section. Correct? Correct. So if you generally remember this formula and remember the Zp value for the rectangular section, you will be directly able to do it. Okay. So what will be the value of your MP? MP is nothing but BT square by 4 into Fy. Breadth is 50, thickness is 10 square, whole divided by 4 into Fy is how much? 250. So on calculation, how much will you get? 5 into 25 divided by 4. Let me write it as 32.51234 into 10 power 4. But he wants into 10 power 4 Newton mm. But the answer need to be in Newton meter. How do you convert mm to meter? 5 into 10 power 4 into 10 power minus. Uh, Hello guys, absolutely sorry for the interruption. Actually, I did not put the system on charge. Yeah, Abdul, my laptop got turned off. So we are back now. So what were we doing? We are trying to find the plastic moment carrying capacity. So as I discussed, MP is nothing but ZP into Fy. Okay. So we had already calculated it. BT square by 4 into Fy, where B is 50, T is 10 square by 4 into Fy is 250. So how much did we get? We got it. We want the answer in Newton meter. Okay, so it was 31.25 into 10 power minus 1 Newton meter. So what can I write this as? 312.5 Newton meter. See, this is a NAT type of question, numerical answer type. So you have to give the answer in the exact decimal places in whatever value he has asked you. Okay. So for this, the answer should be written as 132.5. Generally in GATE exam, they will specify into how many decimal places they want the answer. Okay. So that's your question number 5. Let us move ahead and go on to the next question. So at the location of plastic hinge. So he's asking, wherever you have plastic hinge, what will happen? The radius of the curvature is infinite, curvature is infinite, moment is infinite, flexural stress is infinite. So the correct answer for this question is the curvature is infinite, because wherever you will get the plastic hinge, your curvature is infinite and the moment is equal to, not infinite, the moment is equal to the plastic moment capacity. Okay, so therefore the rotation can be taken as infinite. Okay, rotation can be taken as infinite at your fully plastic section. Right. Next. Question number 7. Which of the following modes of failure is taken care of in plastic design of a steel beam? Generally, what we do plastic design of steel beams, not the elastic design. So when we do the plastic design of steel beams, which type of failure can be taken care of is what is asked in the question. So option 1 says plastic material deformation throughout the beam. Option 2 says lateral buckling of the beam. Option C says elastic buckling of compression flanges. And option D says hinge formation in the beam due to yield of steel. So the correct answer for this is the hinge formation. That's why we call it as a plastic hinge. Okay. So this doesn't come into existence. This is under elastic. This is also under elastic. So the correct answer for this is the hinge formation in the beam due to yield of steel is taken into consideration when we are doing the plastic design of a steel beam. Okay. Moving on to question number 8. So what does it say? As per your code, that is IS 800 2007, the cross section in which extreme fiber can reach the yield stress but does not develop the plastic moment of resistance due to local buckling. See what is happening? Extreme fiber is reaching the yield stress, but what is in turn happening here? It is not developing the plastic moment of resistance. If it develops the plastic moment of resistance, it becomes the plastic section. But here it is not developing, but reaching the yield at the extreme fiber. So in which type of section is that classified under is what he is asking. So here the question is what? Semi-compact section. The answer for this is semi-compact section. Okay. Next question number. This is question number 9. So what are they asking you to us to calculate? Determine the plastic moment of resistance of the I section. So moment of resistance, plastic moment of resistance is nothing but Zp by Zp into Fy. Okay. Now how do you calculate Zp? For calculating Zp, first you have to plot your plastic neutral axis. So generally the plastic neutral axis will divide the section into two equal halves, right? So that is your Z plastic. Okay. So let me know how do you go about this problem. Now what will be the area of this section, area of the total section? Let me first write this depth of this plastic neutral axis. This is nothing but d by 2, or we can call it as 0.5 d, because it exactly divides the section into two equal halves. Now let me calculate the total area. How will you calculate the total area? So 0.4 d into 0.1 d, right? This area. But this area is 2 times. Here also you have that area. Okay. So what we can do, into 2, this value into 2, plus what can I do? This distance. Now how much will this distance be? This will be d minus 0.1 d minus 0.1 d. So that's nothing but 0.8 d, right? So this area will be what? 0.8 d into 0.1 d. Okay, so on simplification, how much will you get the total area? 0.4 into 0.1 into 2, nothing but 0.08 d square plus 0.8 into 0.1, nothing but again 0.08 d square. So 0.08 plus 0.08 is nothing but 0.16 d square. So this will be your total area, right? Now how do you calculate the plastic section modulus? So how do you calculate your plastic section modulus? Individually what I can do is take this area into this distance, right? So ZP, this is just for general understanding I gave. How do you calculate ZP? Take the top area 0.4 d into 0.1 d, and where does the neutral axis for this lie? So see, this much portion is 0.4 d, okay, 0.4 d plus 0.1 d by 2. So that is where your neutral axis will lie. So this will be multiplied by 2. Why? Because at top you have one section, at bottom you have another section. Now this should be added to again this particular portion. How much is that particular portion? 0.4 d into 0.1 d, right? That is the area, into this y bar. So y bar will be 0.4 d by 2. Okay, again this should also be multiplied by 2. Why? Because you have top area, you have bottom area. Or what you can do is, for simpler understanding, call this as A1, call this as A2, call this as A3, and call this as A4. Now in this case A1 is equal to A4 and A2 is equal to A3, right? So your ZP can be taken as 2 times of A1 into Y1 plus 2 times of A2 into Y2. Why 2 times? Because this is equal to this and because this is equal to this. That is how I have calculated this. So your ZP value on complete simplification, you will get this as equal to 0.016 D cube. Okay. Now what will be ZP? What will be MP? MP will be 0.016 D cube into F y. Fy value is not given, keep it this much only. Do we have that option? Yes, we have that option. That is option number D. See, in order to confuse what he has given, I wanted to show you, that's why I calculate the total area. So if you calculate the total area and just multiply it with Fy, that will not be the correct answer. Okay, if you calculate the depth with the total area, that also will not be correct. Okay, so this is the procedure which you have to follow in order to calculate the plastic moment of inertia if you have a I section. Okay, so that's your problem number 9. Moving on to the last problem of 1 mark. These are all 1 mark questions. Nextly, after this, we'll go to the 2 marker questions. Okay, so what does that say? The plastic moment capacity MP, this is nothing but M suffix P, okay, is less than the yield moment, equal to the yield moment, greater than the yield moment, depends on section dimension. Okay, so obviously the answer is what? It depends on the section dimension. Why? Because your ZP is equal to your MP is equal to your ZP into Fy. Fy though is material property, but what is ZP? ZP is A by 2 Fy bar, not F compression bar into F tension bar. Okay, so here if you observe, this is depending upon the section dimensions of the section and how the area is distributed. Not only on the section dimension, it also depends on how the distribution of area of cross section has been done. Okay, right. So that's your 10th question. Now moving on to the 2-mark questions. So this is the first question of 2 marks. So there is a sure shot 1 to 2 marks from the plastic analysis of beams in your gate exam. Okay, there's one definite question. Okay, generally it's a 2-mark question, but it can also be a 1-marker question if it is a direct question. Okay, so if you study the plastic analysis of beams in the steel structures, that will be more than enough to fetch you 1 to 2 marks in your gate exam. Okay, now what does it? The question says, see a simply supported beam of uniform cross section. So there's a simply supported beam. So this has a uniform cross section throughout and the length of this is L and is loaded with a point load P at the midspan. So this is L by 2 and this is also L by 2. What is the length of the elastoplastic zone of the plastic hinge? So we have to calculate the length of the elastoplastic zone. So generally you have a standard formula. What is the standard formula? Length of plastic hinge LP is equal to what? L into 1 minus 1 by shape factor. Okay. Actually, the dimension had to be given. Okay, since the standard dimension is not given, you can take it as a rectangular section because he is telling what? Uniform cross section. Throughout, you make an assumption that it is a rectangular section. Okay, B into D. It has nothing to do, but what is the shape factor for a rectangular section? It is 1.5. So L into 1 minus 1.5. That will be nothing but 0.333 L, nothing but L by 3. Just now we calculated for rectangular section. Right. So that is the distance where the of the length of the plastic zone or the plastic hinge. Okay. So this will be your correct answer. Moving on to the next question. So what does the next question has to say? Very important question this is. Very important question. Question number 2 for 2 marks. From the following figure, for the beam shown in the figure, the collapsible load P is given by. So we have to calculate the collapsible loads. First of all, try to find the static indeterminacy of this structure. So what is static indeterminacy? ds is equal to r minus s. So the number of reaction minus the equation of equilibrium. Okay, so r is nothing but 4. The equation of equilibrium, what we have to, let us neglect the horizontal because there is no horizontal loading on this particular beam. Okay, we are taking only vertical and moments. Okay, so that's why here 2 is gone, here 1 is gone. Okay, so how much will we get? We will get 2. So if static indeterminacy is 2, how many are the number of plastic hinges that will be formed? Plastic hinges required to form a mechanism n. That's nothing but ds plus 1. So ds is 2 plus 1, that will be 3. Okay. So the first, there are two possibilities here. So what are the two possibilities? So say first possibility. So what is the first possibility? Say for example, here one hinge is formed, here one hinge is formed, and at C one hinge is formed. Okay, this is your deformed shape. Okay, so the load is applied at P here. So this is point C, this is L by 2, this is L by 2. Okay, so here this particular portion is what? Delta. Uh, Altaf, hello. Good evening, Altaf. Okay, so here you'll have this as theta and this as theta. Here you'll have the moment of MP. Okay, so this here also you'll have the rotation or moment at the fixed ends as MP. So the first possibility is saying that, what am I saying? The first possibility, the plastic hinge is formed at A, C and B. There's one more possibility, the second possibility. So what does the second possibility say? See, this is very important. So once AC B is the possibility. In the second instance, what I will do is, maybe my plastic hinge is formed like this somewhere here. Okay, this is A, this is B as usual, this is C, but this point is D. Okay, so here my plastic hinge is formed. So second possibility is the plastic hinge is formed at A, D and B. Okay, so now the load is here, right? Here you will have MP, whereas here you will have what? 4 MP. Okay, why? Because this is divided into L by 2, L by 4 and L by 4 portions. Now this side I'll call as theta. So here it will be theta. This side I'll call as alpha. So here. Okay, so here one side it is alpha, the another side it is theta. Right. Now in the first case, if you use the virtual work method, so in both the places I will use virtual work method for easy calculation to calculate the value of collapsible load. So what will it be? The load Pu into the L by 2 into theta. So what is L by 2 into theta? That will be the moment. Okay. So that will be equal to how many moments here? So it will be equal to 2 moments over here, 2 moments over here. Okay. So whereas here 4 moments will be formed. So 4 plus 1 plus 1 plus 1. So total how many? 4 MP plus MP plus MP plus MP. So it will be equal to 7 MP. So what will be the value of Pu here? 14 MP by L. Okay. So in this second possibility case, what will happen? Here also it will be Pu into L by 2 into theta. Whereas here, if you observe, we have 2 MP over here and 5 MP over here. But for 5 MP it is theta, no, alpha, right? For 2 MP it is theta, whereas for 5 MP it is alpha, right? So in this case, your delta on this side will be equal to the delta on the that side. So that is 3L by 4 on one side and L by 4 of alpha on the other side. So alpha will be equal to what? 3 theta. So in place of alpha here I can put as 3 theta. So what will this become? In turn, 2 mp theta plus 3 5 15 mp theta. So 15 plus 2, it will be 17 mp theta. So from that, what will you get the value of pu? You will get 34 mp by L. Whichever is lower, that should be your collapsible load. So which is lower in this case? The lower value should be the collapsible load out of all possible cases. So this is your lower value. So the answer is option B. Okay, I hope it is clear. Moving on to the next third question. What will be the collapsible load of the beam of uniform cross section as shown in the figure? Again, here also what we have to do, we have to calculate the collapsible load. Right, now again go for each span. First I'll do for span CD. Okay, so for span CD, how it will look? This is my point load, this is where my total load is applied, right? So it will deflect like this. So this will be my theta. How much length is this? This length is L by 3. Okay, so since the D is a free end, plastic hinge will occur at what point? At a point C. So again use the virtual work method. So external work done will be equal to what? External work done will be equal to the internal work done. So by the principle of virtual work over here. Okay, so how will you calculate how much is the external work done? Load, that is the W by 2 into the distance into theta. So L by 3 into theta will be equal to the internal work. How much is the internal work? Only one plastic hinge here. So it will be MP into theta. So what will be the value of W? Send everything on the other side. Theta will get cancelled. So if you send everything on the other side, it will become 6 MP by L. Now this is only for the portion what? CD. Now I have to calculate for the span AC. Now for the span AC, how it will look? At B it will come like this. At a C it is simple support. So from here it will go like this. Right? But I am calculating only for the span AC. So here I have a load W, here it is W, L by 2, here it is L by 2, here I'll call theta, here my moment will be MP. Okay, so similarly if I extend this like this, so this will be my theta, this will be my theta, here I'll have one MP, here I'll have another MP. Okay, so again here it's theta, here it's theta. Right, here no movement. Why? Because it is free to move around. Okay, it's free to move around. This will be resisting it. Okay, so in that case, now what will be the external work? WL by 2 into theta minus W by 2 into L by 3 into theta. So this whole simplification will give you WL by 3 into theta. Now this will be equal to the, this is what? This is your external work done. Now this will be equal to the internal work done. How will you calculate the internal work done? How many MPs are there? Here one, here one, here one. There are only 3 MP into theta. So equate this, get the value of W. How will you get? 3 3s are 9 MP here and here theta will go out and here it will be L. Now this is for the span what? Uh, for the span AC. Now what you have to do again, collapsible load is what? Minimum of 2. Okay, so here at for span AC I am getting 9, for span CD I am getting 6. So you have to choose the minimum of both the values. So the correct answer will be option A. See, to in order to confuse you, he has given option A as 9 MPL, 9 MP by L. So these are all by L. Okay, so to just to confuse you, he has given first option as 9 MP by L. Always remember the collapsible load is the minimum of the two loads. Okay, I hope this is clear. Let's go ahead and do the next question. So what does it say? For an I beam, the shape factor is 1.12. So he has given the standard shape factor as 1.12. The factor of safety in bending stress is equal to 1.8, and the allowable stress is increased by 25% of wind and earthquake load. Then initial load factor is 2.016, final load factor is 1.6128, final factor of safety is 1.44, and shape factor will increase by 25%. First, see, he has given all this option. This is a MSQ question, multiple select question. So there may be one answer correct, two answer correct, three answer correct, or all the four may be correct. So we will have to calculate one by one each one of them and see the solution. Okay. So first one, we will calculate the initial load factor. So initial load factor is given by the shape factor, into the factor of safety. Okay, this is bit A. So shape factor is 1.12 into the factor of safety is 0.8. So you will get this on multiplication as equal to 1.01, 2.012. So this is answer correct. Option A is correct. Second, we will calculate what? Now, see, F1 is, no, this is what? Initial load factor. Okay, let it be. Or we will just not give it any name. Now, F1 is nothing but your yield stress by the allowable stress, and this is nothing but 1.8, which is the factor of safety. Now what is telling? The allowable stress is increased by how many percent? 25%. So your new F2 or the factor of safety will be what? Your yield stress whole divided by 1.25 times of allowable shear allowable stress. So how much will this come up to? 1 into 1.8 whole divided by 1.25. So this will come up to 1.44. So now what will be your load factor? In that case, what will be your load factor? Your load factor is nothing but your shape factor again into factor of safety new one. Right? This is your new factor of safety F2 or F new I will take. Okay, F2. So shape factor is 1.12 into 1.44. So how much is this coming up to? 1.6128. Right? So final load factor is 1.6128. This is also correct. Okay. Now how much has the value increased? So what is the new factor of safety? 1.44. Final factor of safety is 1.44. Okay. Shape factor has nothing to do. It will not get increased nor it will get decreased. It has nothing to do with your solution. So this is a multiple select question. So the correct answers are what? A, B and C. You have to select all three. Even if you miss selecting one, your answer will be wrong. Okay, a very good question that you can expect to come in the GATE exam. Finally, the last problem, what will be the shape factor of the given section as shown in the figure. So what you have to do, you have to find the shape factor S or sometimes called as F, which is nothing but ZP by ZE. Okay. Now what you can do is you can assume this to be like a rectangular section, but from the rectangular section remove the circle. So here you have half semicircle, here you have half semicircle. So first let us calculate the ZE. ZE is what? BD cube by 12. No, for ZE I need what? Let me do like this, IXX. Here I'll write. For ZE, I need IXX by Y max. So IXX is what? BD cube by 12 minus the pi by 64 d power 4. What is this? Moment of inertia of the circle. Here half circle is there, here half circle is there. It is symmetrical about the x-axis. So directly I am multiplying it as a circle instead of two semicircle. If you want to do it as two semicircle, you can just multiply the semicircle value into 2. That is also will give you correct answer only. So how much is B? B is 90. D is how much? 90, 90, 30, 30, 30, 30. So total D will be 120 whole cube by 12 minus pi by 64. How much is the diameter for this? Diameter is 60 power 4. Be very careful in the substitution. Okay, you will get 1, 1, 2, 3, 2, 3, 8, 27.45 mm power 4 as I. Now Y max will be what? Exactly half. So Y max will be 60 mm. So your ZE will be what? ZE will be equal to 205397.12 mm per 3. Now what will be the plastic section modulus ZP? So since it is symmetrical section, your ZE, your YE bar and YP bar will coincide, right? They will coincide. Now how do you calculate ZP? So divide this entire area into A1, A2, say A3. Okay, and this is symmetrical. So what you can do, 2 times of A1 into Y1 bar plus A2 into Y2 bar plus A3 into Y3 bar. So instead of 1 and 2 also, this also we can combine. Okay, right? Or you can do it separately, there's no problem. So what will happen? 2 into 90 into 60. Okay, this is 90, this is 60, right? And 60 by 2 will be the Y bar minus pi by 2 of 30 square into 4 into 30 by 3 pi. Okay, for this quarter circle. This is for the quarter circle. So on simplification, how much you will get it? 288,000 mm cube. So finally, what will be your shape factor? Zp by Zd. So 2,000, no, 288,000 whole divided by 205397.12. So this will give you a shape factor equal to 1.4. Directly it is a NAT question for 2 marks. Okay, NAT question 2 marks for gate. So he has asked you to find the shape factor. So directly 1.4, you can give it up to 1 decimal place. The range in the question paper is given as between 1.3 to 1.5. So exact you have to give. So it is nothing but 1.4. So even in whatever range you give in between this, you will get your answer to be correct, and you fetch your full marks. Okay. So I hope the session was very helpful. Right. We'll meet again next Monday. In the next Monday's class, we will be solving the test questions which will be solved next Sunday, right? Sunday on the Ekeeda app, you'll have the test questions. So for bolted and welded connection, so that test questions we will be solving. Okay. So for more details on the Ekeeda app, you can go to the Play Store and download it. Use the code GOLD11 to get complete 3 days access. Or what you can do is you can just contact us on 9029006464 WhatsApp or general message. We will get back to you and help you in whatever doubts you have. Okay. I hope there's no other doubts for today. So we'll wind up. We will meet again next Monday. So the next Monday the class will be for 2 hours. So starting from 5 up to 7 o'clock. Okay. So I hope the session was helpful for you. Please go back and recollect. If in case you are having any doubts in this, you can reach us on the number I told you. We will help you in getting you the access for all the courses on the Ekeeda app. Okay, so this is the number. Bye then, see you next Monday.